However, equation 1 has a limitation on pressure constant. This issue is a serious problem, especially in the case of peripheral that are complex structures, such as various conditions, including temperature or pressure, multiple branches structure, multiple functional groups, or aromatic hydrocarbons. So the support theory needs to link chemical structure related to the equation for estimating the surface tension precisely. Gibbs free energy was used to estimate the property of fatty acid materials, vegetable oils, and bioreactors such as gas chromatographic separation, kinetic viscosity, dynamic viscosity, density, speed of sound, and surface tension bioreactors respectively. For higher pressure in this research, the equation of Pankoston et al. Is developed by using the Gibbs free energy of contribute term to describe in the liquid expansion form change pressure, with the total Gibbs free energy can be rearranged in form of the sum of Gibbs energy from atmospheric pressure and Gibbs energy contribute from the change pressure factor P prime as shown in equation 4. The model factor of carbon atom and double bonds are the representation terms in the difference of molecular structures for each chemical substance, which is a key term that demonstrates in the intermolecular force of sensitivity, chemical properties such as a surface tension. For a reason, the effect and number of carbon atom and double bond term make the model more accurate and can handle for the various types of barrier cells. Following equation 1, the surface tension term of evaluated pressure, which is shown in equation 5, can derive same in the atmospheric term by Gibbs free energy theorem. Substitute equation 1, 5 into equation 4. The final predictive model can be divided in simple linearized model as shown in equation 6, and determination of the numeric constant of equation 6 by multiple linear regression. Determination of average number of carbon atoms and statistical analysis as shown on slide in equation 9, 10, and equation 7 and 8 respectively. As described on the previous section of variable from vegetable oils, they contain a variety of fatty acid methyl ester compositions, which are related to the type of base vegetable oils. In this research, 3 bioreactors from vegetable oil have been measured the mass fraction and characteristic fatty acid methyl ester composition in table 1. From table 1, many various types of fatty acid methyl ester composition of 3 vegetable oil bioreactors have been summarized in average form of number of carbon atoms and number of double bonds in hydrocarbon chain, which this research hypothesis these two chemical structures proposed are key terms to represent the other properties such as surface tension. Therefore, this research focused on these components to develop the surface tension predictive model under temperature and pressure variation. This developed model is based on total Gibbs energy theorem, which explained in the previous section in equation 6. The coefficient in linear form of the model at different temperature and pressures and are evaluated by the multiple linear regression in table 2. The predict surface tension of the proposed model was compared with the experimental data of 3 bioreactors at 5 various points of pressure and temperature. It was demonstrate the model mismatch in terms of percent AAD in table 3 to 5. The canola bioreactor result in table 3, which had a higher ND 1.28 and slightly low stack average 18.03 is present the lowest overall percent AAD average at 1.6%, while the soft-nut bioreactor in table 5 had the lowest of ND 0.93 and higher set 18.67 7 gives the highest percent AD at 3.19%. Generally, the high fat and ND give the high percent AD due to the unpredictable structure of long-chain molecule and double bond located in the model. However, the sample cells in this research has the double bond location not complicated in the various carbon atoms. Figure 1 to 3 are variability graphical method of each sample cell, which compare between predict data and experimental data. The derivation result compared with exact line show the lowest derivation lower than 5% in canola cell in figure 1 and the highest derivation lower than 10% in jatropha cell figure 2 and soft cell in figure 3. The assessment of compatibility of the model can summarize that proper for these three sample cells due to the criteria of percent AAD, the derivation result, and the coefficient of determination result. Finally, the overall percent AAD is used as key factor to compare with the previous study predictive surface tension model, such as Pangoson et al. In case of atmospheric pressure and Shehetri et al. In case of evaluate temperature and pressure. The proposed model should be selected according to the overall percent AAD equal 1.67% at atmospheric pressure case which is lower than result in Pangoson et al. 13.94% and the overall percent AAD equal to 2.58% at evaluate temperature pressure case with lower than result in Shehetri et al. 6.18% C in table 6. In the part of conclusion, the proposed model based on the total Gibbs energy theorem is used as an aspect model in order to compare in model accuracy and train with the two previous studies in predictive surface tension model of case study atmospheric pressure and evaluate temperature and pressure. Three berry cells, which are canola berry cells, jatropha berry cell, and soft nut berry cell, are used as samples to measure to surface tension at various temperature and pressure. With the comparison results given by the proposed model, it can be concluded that the predict surface tension by the average number of double bond and atom carbon of proposed model provides the suitable accuracy of percent AAD under atmospheric pressure and evaluate temperature and pressure more than previous study due to the limitation of previous model. The results have shown very good accuracy of the proposed model in various temperature and pressure with the criteria of percent AAD, deviation result, and the coefficient of determination result. And the last, the model must be verified in accuracy with other case of evaluate temperature and pressure and other variable biocell surface tension for ensuring the model accuracy. Thank you for your attention.
Thank you very much for the Ms. Chapat for the presentation. So it's time for discussion. I will read the question in the chat box. So the first question is for Mr. Eric Prasetyo. And Mr. Eric Prasetyo, did you still together with us?
Of course, I'm still here. Okay. Should I read the question or?
Okay, I will read and then you can answer.
Sure.
Why did you use the acetic and tannic acid for the leaching of cobalt and lithium compared to the strong acid like HCl, H2SO4 or another else? What is the role of tannic acid of the leaching process, and does tannic acid form complex with the leaching metal cation? So you can answer now.
Okay, first thank you Mr. Hans for the question. Why we choose tannic acid and acetic acid compared to the stronger acid? Because we consider the hazard and also the toxicity of these both reagents are less than to the stronger acid. And we also guess that in the how to say, if we scale up our findings to the pilot plan, we expect that tannic acid and acetic acid would be less dangerous, less dangerous to the human, also to the equipment compared to strong acid. And the second question, the role of tannic acid is as a reductant, because in the lithium battery, the cobalt form is trivalent metal, which practically insoluble. So to make it soluble, we have to reduce it into divalent cobalt. Okay, I think that's the answer.
Okay. And the next question, Mr. Hans Christian, is there more question for Mr. Eric?
I think that's enough. Thank you.
Okay. And then the second question from Egi Agustian for Miss Nichapa is about the water contents. How about the water content in the biodiesel? Is there any effect in your experiment like that? So you can replay your answer.
Yes, thank you for your question. In the generally, the effect of the quality biodiesel, including moisture content, water content, one, or catalytic loading, or or molar ratio between the oil per the alcohol, and the water content is affecting of the quality biodiesel, so concentrating, because the water content make the biodiesel portion generate to the soap and composition of the fatty massive ethyl ester. In this research is methanol used to alcohol. Thus, the water contents affecting to the composition of biodiesel portion, so affecting to the accuracy of the model also. The model is not accuracy because the fatty acid methyl ester has a different composition. I explain the slide. I can explain the slide. May I share the slide?
Yeah. Maybe Mr. Kiki, can you help to show the slide?
May I share the slide on my computer? Yeah, okay. So this the fatty acid methyl ester in the biodiesel. Thus, the water content has the most. This is affecting to the fatty acid methyl ester in this. Clear? Yes, finished.
Okay. You finished? Okay, thank you. And after finish, there is more question again from Mr. Jody. Maybe your topic is interesting, so a lot of question. So for the second presentation, to get the coefficient of the equation using what method? What the method do you use for to get the coefficient, and what is the expected percent EED value in this research? So
in the second topic, I can generate coefficient this by multiple linear regression method under experiment data at atmospheric pressure and at various pressure, and I analyze the percent AAD is shown slide, surface tension experimental, and surface tension predict. Yes, I'm finished.
Okay. Okay, thank you very much for your answer. Yes. Maybe just remain 4 minutes, but I would like to ask for Mr. Hans Christianto. So, may I know, instead of the leukinacid, is there any other materials we can use? Or have you ever do another, maybe the biomass or another materials before? Thank you.
Okay, thank you for the question. Actually, the research regarding green synthesis is kind of hot topics these days, and many sources of extract is used from the extract, materials from fruits, fruit peels, leaves, roots, etc. is used. So there's no strict limitation for the source of the biomass. That's my answer. Thank you.
Thank you. Thank you for the presenter for this part. So maybe we can continue for the next. Will be two presenter again, Mrs. Wita Kartikarestu and Miss Ruli Retno Mawarni. Before I show in the video, I would like to confirm for the presence of the Miss Wita Kartikarestu.
I present today.
Okay. This Kartikarestu will present the topic about the effect of the acid solution on the properties of isolated lignin from black liquor of oil palm empty fruit punch or OPFP pretreatment. So we can see the video now for the presentation.
Thank you, moderator, for giving time. Today I would like to present our research titled The Effect of Acid Solution on the Psychochemical Properties of Isolated Lignin from Black Liquors of Oil Palm Empty Fruit Punch pretreatment. And then this is our outline. At first, the introduction, method, result, and discussion, and also conclusions. For introduction, lignin is a three-dimensional network polymers that use as surfactants, adhesive, antioxidants, dispersant formulation, including absorbents, dyes, paints, and then phenolic resins. And lignin can be isolated from black liquor, in which the lignin separation itself is the main factor for a high economical lignin cellulosic biorefinery. And the black liquor itself is a complex mixture in which consists of water, organic and inorganic substances. And black liquor also composed of 65 until 85% of solids and 10 until 50 heavy lignin for the percentage. And the background for this research, due to the difference in raw material resources and also the isolation methods, can influence the structure and cytochemical properties of the isolated lignin. And we would like to utilize the byproducts of cellulose production from PEFG, the black liquor, from the biorefinery process in the research center. Therefore, our objective is to determine the effect of acid variation on the physical and chemical properties of lignin obtained from black liquor of alkaline treatment, oil, palm, and the food branch. And here is our method. The first one, the material itself composed of black liquor, sulfuric acid, hydrochloric acid, sodium hydroxide, and then aqueous. And the preparation of the lignin isolation itself is by using the acid, whether sulfuric acid or hydrochloric acid, to precipitate the lignin in the black liquor. And then we have the target pH of 2, 3, and 4, and then stirring for 8 hours and then leave for night. And next day we will do the filtration and then also washing with warm aqueous until the pH reach the aqueous pH around 5 until 6. And then next one is put into the batteries to and then put it to be dried in the oven at 50 degrees Celsius for 24 hours. And the next day we will have the products that is isolated lignin that's ready to be pulverized. And then here is the result regarding the yield and then the lignin content of the isolated lignin. All the 7 samples have the same yield around 1%, and the lignin content that varied from 38 until 90%. And then the lignin content was increased when the degrees pH from 4 until 2, and then this is also with the accordance to the other research from other researcher. And then based on our result, it can be stated that the significant difference in lignin content from different acid due to the source of the black liquor, because sample 1 and 3 same source but different with the sample of 4 until 6. Therefore, we did the sample 7 in which the same source with the sample 4 until 6. And after using the same source, it resulted quite similar result, 90 and 86. Therefore, the source of the black liquor also play important roles in here. And next one is the morphological analysis, in which the decrease in pH resulted in difference in particle size and distribution, as we can see from the figure in the morphological analysis. And then the particle distribution also different. And then the particle size ranging from 10 until 200 micrometers for all the isolated lignin. So the distribution will varies both from sulfuric acid and also hydrochloric acid with different pH. And here is the particle size analysis, in which the highest lignin content, that is lignin with pH 2 in sulfuric acid, and then also lignin pH 2 from the hydrochloric acid, which both of them resulted in particle size twice than the commercial lignin. So the technical lignin have the particle size larger compared to commercial lignin. Okay, for the next one is the functional group analysis, in which the spectra of the lignin isolated by various acids with different pH are similar, even though from different sources, and resulted in different lignin content or purity. The obtained lignin has similar spectra. And the different percentage of the lignin content or the purity might be due to some impurities or other compounds exist in the samples, and also from this functional group spectra, we can state it that the general composition of the lignin is not affected by the type of acid and targeted pH, because the lignin, the obtained lignin has the similar spectra, whether from hydrochloric or sulfuric acid. And here is for the conclusion, in which the isolated lignins that separated from black liquor by using acids such as sulfuric acid and hydrochloric acid at different pH was successfully synthesized. And then also the isolation treatment with hydrochloric acid resulted in higher lignin content compared to sulfuric acid, that it might be influenced by the source of black liquor as the raw material, and also by the hydrogen bonding that occurs in the process. And then also the isolated lignin samples show various particle size and quite well distribution. And then the two kinds of lignins with high purity have particle size twice higher than the commercial lignin. And the spectra from the functional analysis of the isolated lignin show that the bands of the spectra are similar. And then from the data that we get, it is needed to have the further studies in which the method that resulted in the higher lignin yields, and then also the lignin content. That's all from my presentation. Thank you very much. And we'll go back to the moderator for the next session. Thank you.
Thank you, Ms. Vita, for the presentation. And next, we will see the video presentation from the Ruli Retno Mawarni. Before that, I wanted to check. I wanted to confirm that Ruli Retno Mawarni is already come to our Zoom or not. Okay. Is there any Ruli Retno Mawarni in this room? Because if you cannot attend this room Zoom, so we cannot play your video. So okay, so maybe
Honorable Committee of International
because Miss Ruli Retno Mawarni is not here, so maybe we cannot play the video, and then maybe we have to skip the video, and then we just have one presenter for this part. For yeah, so only Miss Vita Kartika Restu. So maybe come to the discussion session directly. Oh, it's coming or not? Sorry. Is it Miss Retno Dita? No? Okay, we will still wait for the Ruli Retno Mawarni.
Yes, I am.
Ah, okay. Okay, so maybe we can start the video now.
Okay. Symposium on Applied Chemistry, ISEC 2021. Ladies and gentlemen, good morning. In this morning, I would like to thank you for the opportunity that has been given to me for presenting the paper. Please allow me, Ruli Retno Mawarni, and my team from Institut Teknologi 10 November Surabaya for presenting our paper with the title Simulation of Triacyl Glycerol Separation from crude calopulum inoculum oil with batch-wise solvent extraction method. I'd like to begin with an information about our subject called nyamplung. Nyamplung or calopulum inoculum is a large evergreen plant commonly called tamanu, beach calopulum, maswood, or beautiful leaf, also known as a plant having many uses. However, the use of this plant is still limited because inoculum oil contains dangerous poisons when consumed. So it is generally used and studied or as a raw material for biodiesel. Inoculum is a forestry plant that began to be planted in Indonesia in 1950 as a coastal protector from abrasion, wind breaks from sea to land, tidal wave barrier, riverbank, beach barrier from landslide, and brackish water quality guard. If we develop calopulum inoculum, it will be good to protect Indonesia's nature while making it a coastal resort. The research subject is calopulum inoculum or nyamplung. Calopulum inoculum seed oil contains a quite large triglycerol or TAG, so it can be derived to be vegetable oil after removing the impurities. The requirement of vegetable oil is containing high of TAG and low contaminants such as free fatty acid or FFA. In previous experiment, we found a Paramartha in 2016 success for experimenting with making nyamplung to be vegetable oil using batch-wise solvent extraction method. This method obtained the TAG from experimental data was 98.56% and FFA from experimental data was 0.35% after 8 stages. The BSA method has success in removing contaminants and increasing the TAG level so that it meets the requirement of edible vegetable oil. The objective of the research. So the objective of this study was to simulate the purification of TAG from calopulum inoculum crude oil to become vegetable oil with batch-wise solvent extraction or BSE by using the Aspen HYSYS V10 application. Hereafter, the simulation finding the appropriate binary parameter coefficient and compares the result with the experimental data from other literature in previous publication. The experimental, the fluid package then we move to the experimental. In Aspen HYSYS, we use fluid package and binary interaction parameters. Fluid package that we use was Uniquark and NRTL because these are suitable for liquid-liquid equilibrium. So binary parameter we use are LLA unknown only, LLA all binaries, and immiscible. In figure 1, we can see system circuit on pure solvent extraction in pre-simulation. After that, we go into real simulation. This is one stage for the system. This is the real simulation. We have 8 stages for simulation system. We can solve for the inlet. We have crude oil from calopulum inoculum with mixed with the solvent hexane, then mixed with methanol in the tank, and then goes to the decanter. It happened for 8 stages. Until the last. We did it like the experimental did. So hexane in the solvent is a food grade, so we don't need to worry about poison that contained in the hexane. And this is the result. The result, we can see the dots. With the yellow dots, it's experimental data. And then we find in the 3 fluid package, we found that LLA unknown only is near with the experimental data. It has error less than 1%. This is comparison of triglyceride purity of simulation and the experiment. So from all I talk about, this is the conclusion. Simulation of TAG purification from crude nyamplung oil using the BSA methods can be modeled with Aspen HYSYS V10 application. Using the unique walk and RTL fluid package and 3 binary interaction parameter, there are LLA unknown only, LLA all binaries, and immiscible. The most suitable type of binary interaction parameter to be used in the simulation was LLA unknown only with the unique walk fluid package with a simulation error of less than 1%. The AG purity is 98.53% in the simulation and 98.56% in experimental. Thus, research proved that from the simulation by Aspen HYSYS V10 application, purification of Calophyllum inoculum seeds can be used as vegetable oil. That's all about my presentation. Thank you for nice attention. I will be ready to answer the question and discussion. Thank you very much.
Thank you, Ms. Ruli, for your presentation. Okay, we will still wait for the question from Ms. Vita and Ms. Ruli, because in this part we just only have 2 presenters. So you can write the question on the chat box, or you can directly ask the question to the presenter. Okay, is there any question? Maybe I will ask the question. It seems like the duty of the moderator have to ask the question. For the Miss Vita, it's very nice presentation, but I would like to know, you use the sulfuric acid and folic acid for the treatment of lignin. Both of them is the strong acid, but why the result is a little bit different between the folic acid and sulfuric acid?
Thank you, moderator, for the questions. Actually, the using of 2 strong acid based on literature study, and then the difference, the lower result was affected by the source of the black liquor, because at first for the sulfuric acid that we use the first source, it might be the precipitate is not as many as the second source. So that's why in the second source that use the hydrochloric acid, it resulted in higher lignin content. That's why we try again the additional experiment using sulfuric acid, and then get the lignin content quite similar, 86 for pH 2, and then for previous one for the hydrochloric acid, we got around 90. So that's why we can state that the source of the black liquor also plays important roles beside the concentration of the acid itself. That's from our experiment.
Thank you for the answer.
You're welcome.
And then we still wait for another question. Is there any question more for the from the participant? Okay, then I would like to ask to the Miss Ruli. For the Miss Ruli, I see in your presentation you simulate using the hexane for making biodiesel, isn't it?
Yes.
So actually, I didn't catch what is.
Pardon me. Pardon me. Sorry, my internet connection.
Yes, 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 that's okay. Actually, when I see your presentation, I see that in your simulation you use oil, methanol, and hexane for making biodiesel.
Yes.
So, but actually, I didn't catch the idea. What is the purpose you use the hexane? Is it just for solvent?
Okay, thank you for the question. So we used to solvent in our simulation because in the experiment used to solvent, we separate the crude color film inoculum based on the polarity. So we use methanol for polar and we use hexane for non-polar.
Okay, thank you for the answer. And is there any more question? So maybe because there is no more question, so I would like to close this session. So you can join again for the next session at 3:15. But please ensure the Zoom ID is correctly written within the format after you relog in into the Zoom meeting room. Okay, thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Miss.
Thank you so much.
as one of the most dynamic and innovative companies within the Berke Group. Has been in business for over 17 years and has established itself as the major player in the research and the chemical analysis industries. Its customers include many bodies in the government sector, as well as large corporate
Assalamualaikum warahmatullahi wabarakatuh. Bapak Ibu sekalian, ladies and gentlemen, we will start the parallel session 8.2 right now. First of all, I would like to welcome you all to this presentation. And in this occasion, I would like to introduce myself. My name is Roni Mariana. I am a researcher at the Research Center for Chemistry, BRIN. Ladies and gentlemen, we have 6 presenter. And before we begin, we will begin shortly. Firstly, Mr. Dimas already with us. Mr. Dimas, are you? Oh, okay, thank you. Mr. Kiki, are you with me? Mr. Kiki? Okay, we will prepare the video first.
Baik Bapak Ibu sekalian, Mas Kikinya sudah siap. Thank you Mr. Kiki. Ladies and gentlemen, dear participants, we will begin this session. This session will be consist of 6 presenter, and then after that we will conduct the discussion session. Please ask your question by writing in the chat room, or you can also ask directly in the discussion session. Mr. Kiki, we are ready. The first presenter will be Mr. Dimas Agung Setiaji.
My name is Dimas Agung Setiaji, and I will present.
Okay, go ahead.
Presentation about my paper with the title of Study Mechanical Properties of Polyurethane Foam caused by chitosan reinforced calcium carbonate with temperature curing variation. Okay, with some keyword: polyurethane, foam, chitin, chitosan, and calcium carbonate. This paper is a purpose for making some headliner for the car. We know that some manufacturing for make some high density polyurethane foam is little bit expensive. Therefore, we make some innovation with using some chitosan, which is marine waste, that we can use it for a coating, and some calcium carbonate, which is good for a filler, and the result is cheaper than high density polyurethane foam. Okay, next. Some introduction. First, polyurethane. First, polymer. Materials that are experiencing rapid development. We know that polymers is useful around the world, and we can see anywhere. Yes, can be applied for industrial, household, automotive, and for example, for headliner for the car. Next is one of the type from the polymer is polyurethane. The basic ingredients for making polyurethane consists of diisocyanate, polyol, and James extender for additive. And the third, we use chitosan. What is chitosan? Chitosan is some marine waste that we can find it in the skin or a shell of a crab and shrimp, useful for increasing the density value of the material. And the last one is calcium carbonate. Calcium carbonate is work as a filler in polymer material and making a polymer material become more rigid. With some experimental. First one is material. First, we meet with virgin polyurethane foam with standard name GIS A6400, and then chitosan, and the last one is calcium carbonate. Next, for coating processing, foam with this test specimen size with that standard was immersed in calcium carbonate for a filler purpose. And the next one, for coating purpose, we use some immersion with chitosan and let them soak. Therefore, the both chitosan and calcium carbonate can be absorbed perfectly. And the last, we put it in the oven with 60 degrees Celsius for 30 minutes for the basic the basic heat and the basic time for a current purpose. We use it for some variable, and we can see it at the table in the next slide. For the characterization, we use compound content, FTIR, and morphology with FESAM, and mechanical testing with UTF and elongation. This is some sample code for characterization. We played with some virgin foam, and the variation is about curing time and curing temperature. Okay, next. We can see that FTIR result for a compound content. There are no different, it's very significant. The compound content between polyurethane virgin foam and the composite foam using a mixture about with titosan and calcium carbonate, it's not much different. Okay, so there are no unwanted side effect of term of chemical. It's safe. Next, we can see that morphology form. The circle one, the sticker icon, is for information about layer of the edge of the foam surface, and the square icon is information about film on the pores. You can see that some layer is covered in a pore of the foam, which is good result for each sample. And the last result is about mechanical properties for the material. The left one is UTS and the right one is elongation. We can see that best shear resistance value was obtained from polyurethane foam with the addition of titosan and calcium carbonate. That with curing some more about 100 degrees Celsius with time in 120 seconds. 120 minutes. It's like 2 hours. And the same result with elongation with the same sample too. And a conclusion, there's no much different about virgin and the composite foam, which is it's a good sign. There are no unwanted side effect in the term of chemical. And the result of morphology test, it found a layer that closed the surface pores after a polyurethane foam was added with titosan and calcium carbonate. The layer is provide an increase the rigidity and toughness, and we can see it with UTS and the elongation. With some mix for about titosan and calcium carbonate with bond in the form of NH and CO bond, which strengthened the bond in the composite foam. That's all about my paper. Apologies with my bad accent, and thank you.
Okay, thank you, Mr. Dimas, for the presentation. The next one will be my colleague, Miss Amanda. Mr. Kiki, please start the video, Miss Amanda.
I would like to share one of our project about the production of starch biofoam reinforced with microfiber cellulose derived from oil palm empty fruit bunch. My name is Atanasia Amanda Stefani. I am from Research Center for Chemistry. So, food packaging is one of the essential items in our daily life. And one of the type of food packaging that is often used is styrofoam because it is lightweight. It is also has the great mechanical properties and affordable. However, the use of styrofoam as a food packaging is not recommended because it is not only harmful for humans but also for the environment. That's why it is very important to find an alternative, for example, starch-based biofoam that is more eco-friendly and safe. Nevertheless, the current studies show that the starch-based biofoam still pose low mechanical properties. That's why further modification and improvement, for example, via inclusion of reinforcing filler, is important to be conducted. In our Center for Chemistry, we have successfully produced very large-scale production of microfiber cellulose derived from olive palm empty fruit bunch at the capacity about 100 kilogram per day. So this microfiber cellulose is a potential to be used as the reinforcing filler in the modified starch-based biofoam to enhance the mechanical properties as well as maintaining the eco-friendly characteristic and providing the best degree of degradation. So the aim of this project is to understand the effect of microfiber cellulose derived from oil palm empty fruit bunch as a promising reinforcing materials to enhance the performance of starch-based biofoam. We characterize such as physical properties, functional group, morphology, and biodegradability of the obtained starch-based nanocomposite. So this is the methodology. Consists of first isolation of microfiber cellulose from oil palm empty fruit bunch, involving the lignification and bleaching process, and then followed by the characterization of the obtained microfiber cellulose. After that, we prepare the foams from starch tapioca, as well as the nanocomposite starch reinforced with microfiber cellulose with varied concentration from 2% to 10% wood. And we blend all the formulation and do the hot pressing to get the final foam product. After that, we do the characterization of the obtained biofoams. So here are the results. In terms of the density, we can see in this table that we can maintain all of the density of the formulations at about 0.33 gram per centimeter cubic. And it is important to maintaining the density because we can clearly investigate the effect of microfiber cellulose in the performance of biofoam composite. So here is the FTIR result. You can see from the graph that basically both the neat foam of the starch is comparable to the composite foam reinforced with microfiber cellulose, that both of them show the typical starch biofoam. For example, at the bands of 2,900 corresponds to the CH stretching, and at the band of about 1,100 corresponds to the CO bond stretching. And the differences between these two characteristics of the meat without the cellulose and the composite with the cellulose is that in the wide band of about 3,300, which is correspond to the OH1 stretching. There is a reduction of the band OH stretching in the composite, showing that the existence of the hydrogen bonding interaction between the starch and the film, which is microfiber cellulose. These results show that the compatibility between the starch and cellulose to form a compact molecular structure in the biofilms. So this is the mechanical properties. We can see in here that the addition of the microfiber cellulose above 500 show the improvement of the tensile strength, and it is optimum at 7% of the microfiber cellulose inclusion, with the result an improvement about 88% comparing to the styrofoam, and even reaching up to 170% comparing to the neat starch biofoam. So the next one is the result for the morphology. You can see in here that FO, which is a neat form of the starch, show the regular structure morphology, while when we edit the microfiber cellulose, there is a disturbed morphology with the irregular pores and a bigger size pores. It is also confirmed clearly confirmed in the SEM micrograph that the addition of microfiber cellulose it actually disturbs the surface morphology of the biofoam composite comparing to the neat foam without microfiber cellulose. However, it is interesting to know that this influence does not affect the mechanical properties of the biofoam. And it is shown that actually microfiber cellulose as a strong mechanical reinforcing filler can significantly enhance the mechanical properties despite the effect of inhomogeneous morphology in the surface of biofoam composite, perhaps due to the non-homogeneous blending process that maybe further we can improve the blending process. So the next one is the biodegradability. The degradation test was carried out by burying the biofoam composite in the soil for several days. So from this result, you can see that from this photograph that biofoam actually started to degrade since day one and completely degraded from this graph after 5 days only, which is a very short time. So this result showed that this system of the starch biofoam reinforced with microfiber cellulose is a potential and promising of the biodegradable food packaging. So to sum up, we have investigated the effect of microfiber cellulose inclusion into the starch-based biofoam, and we can see that the addition of microfiber cellulose can significantly enhance the mechanical properties while maintaining the biodegradable characteristic and of course eco-friendly, and it is also cost-effective process to give a promising system as a food packaging in the future. So I would like also to thank the financial support from PT Mandiri Palmira Alpindo, as well as thank you all for your kind attention. Thank you.
Thank you, Ms. Amanda, for the nice presentation. Ladies and gentlemen, we will continue to the presenter number 3. This is also my colleague, Pak Jody Arya Laksamuni. Mr. Kiki, please start the video.
Thank you for this chance. This is an honor to be able to present the result of our research Our research topic is about the adsorbent characteristic of the polyphenol alcohol, zeolite, and activated carbon on desalination of seawater. I am Jody Arya Laksmono here as a corresponding author and the presenter. Water scarcity is recognized as one of the most important concerns in many countries, including Indonesia, with some of its regions experiencing water shortage so far in some of area in Indonesia. The availability of clean water only relies on the water in the rainy season. The increase in the world's population has an impact on increasing the needs for access to clean water sources. But along with the drastic climate change, the scarcity of clean water is increasing. Therefore, alternative efforts are needed in providing clean water. According to the World Health Organization 2019, water needs 30 liters per day per individual, consists of 20 liters per day for sanitation and 10 liters per day for drinks. Indonesia, with a large population here, only around 50% of the total population has access to clean water. Indonesia is in a archipelago. Looking at the marine waters area of Indonesia, it has water resources that can be processed into clean water, especially for urban, rural, and remote areas that have difficulty accessing clean water. As we know that many technologies implemented for the desalination of the seawater. Commercial desalination technologies include multi-stage flash, multi-effect distillation, membrane-based technology, electrodialysis, and capacitive deionization. However, the commercial desalination technologies using a high energy consumption. In this research, we provide the technology which is low cost operation, low energy consumption. In this research, we provide the absorption technology to providing the fresh or clean water from the seawater desalination. The purpose of this study was to determine the role and phenomenon of the absorption. Here we use polyphenol alcohol, zeolite, and activated carbon in the seawater desalination process on a fixed bed absorber column. In this methodology of the research, we used some of material here, including adsorbent, polyphenol alcohol, zeolite, and activated carbon, and also argentometric reagent, and then salt solution with concentration 2, 2.5, and 3%. Absorbent, we have to preparation in the first method here to remove the water content in the absorbents. And then we have to absorbent characterization using PET. We can analyze the pore size, surface area, and pore diameter. And also same morphology. Absorption test. We use the fixed bed absorber with 4 milliliter per minute flow of flow rate, and then weight variation of absorbent are 50, 75, and 100 gram. And also absorbent concentration is about 2, 2.5, and 3%. Sodium analysis using argentometric method, and then the absorption analysis using Young-Nelson method. From the physicochemical characterization using BET, analysis, we have to solve that the PVA has a lower surface area, and then zeolite is moderate, and the activated carbon is higher. In general, PVA as a biodegradable polymer has few pores. Furthermore, the pore volume of activated carbon value is higher compared to zeolite and polyphenol alcohol. This indicates that the activated carbon has a large number of pores that can be used during the adsorption process. From the BET result shows that the pore size between the adsorbent is almost uniform in the size range around 2 nanomillimeters. However, PVA has a higher hydroxy number value than zeolite and activated carbon. This indicates that the PVA has more hydroxy groups than zeolite and activated carbon. From the morphology of adsorbent shows that the PVA morphology was non-porous. This confirmed to the result of PVA surface area test using BET. However, PVA is higher hydroxy number than other adsorbent, which is very useful for adsorption process by utilizing the hydroxyl groups on the PVA surface. Zeolite has an irregular and porous surface, some part of crystal with tetrahedral structure. Meanwhile, activated carbon for morphology has many particles with such particle having several pores. This causes the AC or activated carbon surface has many pores. Then we study about the effect of the adsorbent type in various adsorbents, mass, at salinity concentration 2%. From the figure A and B, that we can show that the amount of the adsorbent is 50 and 75 gram respectively. PVA has optimal effectiveness in reducing seawater salinity compared to zeolite and activated carbon. According to the physicochemical properties, the hydroxyl number of PVA is higher than zeolite and indicates activated carbon. Indicates that the number of hydroxyl group on the surface of PVA is more reactive than the zeolite and activated carbon. So that the PVA surface which have a hydroxyl group play a role in the adsorption process of sodium ions in seawater. An interesting phenomenon occurs as adsorption process with total head 100 gram adsorbent. The performance of PVA decrease the adsorbed sodium ion and inversely increase in zeolite and activated carbon. In this process, the indication of adsorption process is the desorption mechanism according to the character of the zeolite and activated carbon. However, the result showed that the zeolite was more optimum in reducing seawater salinity due to the result of morphology of the activated carbon, which is have a micropore, mesopore, and macropore in the activated carbon surfaces. The implication that the selectivity of activated carbon is not better than the zeolite. So the zeolite is better selectivity than activated carbon in reducing seawater salinity. We also study the effect of adsorbent type in various salinity concentration at 100 gram absorbent mass. In this case, for the observation of 100 of absorbent is due to the interesting phenomenon. That figure provides information performance of each adsorbent on the salinity concentration. In general, it can be explained that the increase in salt concentration increase the performance of PVA adsorbent. However, zeolite performance decrease inversely with meanwhile, AC or activated carbon tends to be more stable. A high salinity concentration indicates a high sodium ion density. Therefore, the salt ion distance is higher compared to the low salinity concentration. As a result, at high salinity concentration, the number of sodium ion around the adsorbent is higher than at low salinity concentration. In this case, the zeolite surface will attract positive ions through van der Waals attraction and repel negative ion through electrostatic repulsion. Regarding to the physical chemical table in before, characteristic of PVA has higher hydroxyl number than zeolite and activated carbon, which imply to the number hydroxyl group on the surface of the PVA. The electronegativity of hydroxyl groups will increase with the increasing number of ion around the PVA. Conversely, the performance of zeolite is at increasing salinity concentration will decrease. In fact, the reactivity of alumina group of zeolite has good performance at low salinity concentration. Meanwhile, hydroxyl group will show increasing reactivity with increasing salinity concentration. The conclusion is PVA, zeolite, and activated carbon each have a potential to reduce seawater salinity according to their physicochemical characteristic. At the amount of adsorbent 50 gram and 75 gram, PVA has optimal absorptivity in the process of reducing seawater salinity through chemisorption mechanism. Meanwhile, the use of the absorbent amount of 100 gram zeolite has more of the optimal absorption activity than PVA and AC using physisorption mechanism. At higher salinity concentration, the performance of PVA adsorbent also increased. Meanwhile, zeolite decreased activity and AC was not affected by variation in salinity concentration. Thank you.
Thank you, Pak Jody, for the presentation. Okay, the next presenter is Miss Cynthia Lauren Santoso. Mr. Kiki, please start the video.
Assalamualaikum. Before I start my presentation, let me introduce myself. My name is Cynthia, and today I will present about my paper. And the title is The Effect of Catalyst Concentration in Polylactic Acid Synthesis from Lactate using Candida rugose and DMA or dimethyl acetamide solvent through ring opening polymerization. This is the outline for my presentation. This presentation will be given in the 4 parts. The first part concerns about the introduction, and then discuss about experimental, and next discuss about result and discussion, and finally this conclusion. Okay, let's move to the part 1, introduction. Recently, plastic has become an environmental issue due to long-term degradation. One solution for this issue is using bioplastic or PLA from renewable material. Some advantages from PLA are degrading in the short term, stable, and good mechanical properties. There is some requirement to obtain the advantage of PLA, and the requirement is having a high molecular weight and non-toxic, especially for humans. To reach this requirement, there is some concern about PLA synthesis. In the synthesis process, it will be safe using green catalyzed, non-toxic solvent, and using ring opening polymerization to reach a high molecular weight of PLA. Lactate can be used as a raw material for PLA synthesis. PLA is a thermoplastic polyester that has carbon asymmetric on its structure. PLA itself has three different types of polymer. There are poly-L-lactic acid or PLLA, poly-D-lactic acid or PDLA, and poly-D-L-lactic acid or PDLLA. From three types of this PLA, PLLA has many advantages compared with the other, and the advantage of PLLA has been mentioned in the previous slide. The purpose of PLA synthesis is to obtain the high molecular weight of PLA. The higher molecular weight, PLA mechanical properties become more compact. There are other material uses for the PLA synthesis process. There are Candida rugose as a green catalyst and dimethyl acetamide as a solvent. The consideration using Candida rugose as a catalyst is easy to find, stable, and could be used for esterification reaction, non-pathogen, and characterized as a green catalyst. And also for dimethyl acetamide solvent, categorized as a non-carcinogen and non-toxic solvent. In the second part, I will present about my experimental. For synthesis preparation, lactate, dimethyl acetamide, and Candida rugose are used as a raw material. And for the independent variable are catalyst ratio, which are 2%, 5%, and 10% weight catalyst per weight lactate. This is the polymerization process. The polymerization process was conducted at temperature 80 Celsius for 3 days. After the polymerization process, the solution was cooled until it reached room temperature, and then the chloroform was added to the solution. Candida rugose in the solution was separated using vacuum filter. Polymer product will be characterized using NMR to determine PLA structure as well as for estimation of lactate conversion and number of first molecule weight or Mn of the PLA, and GPC to determine the molecular weight of PLA. Okay, next I will present about my experiment result and discussion. This is a sample appearance after polymerization process. In the second row, show polymer solution appearance, and the third row show Candida rugose appearance on filter paper. As you can see, Candida rugose after the reaction has a light brown or yellowish color. This color indicates that Candida rugose is not denatured. And the more concentrated catalyst ratio, polymer solution color become more intense. And when conduct the process, it was observed that viscosity of the polymer solution increased and indicate the molecular weight of PLA also increased. This is result from NMR in a spectral form with sample to percent catalyst ratio. The spectra show a chemical shift at around 1.6 ppm indicate the methane group bonding. The chemical shift at 5.13 until 5.24 ppm could be described to the hydrogen multiple bond which represent PLA main chain. The chemical shift at 4.3 until 4.4 ppm represent the hydroxyl group of PLA located at the end of PLA chain. And the last one, the chemical shift at 2.13 ppm, 2.97 ppm, and 3 0.05 ppm are the peaks of dimethyl acetamide solvent. This chemical shift that I mentioned before indicate that there are presence of PLA. From the NMR spectra result, the data can be used for lactate compression using this formula on the right side, where integral of lactate, PLA, and PLA chain has been mentioned in the previous slide. Not only to calculate lactate conversion, the data from NMR can also calculate the number average of molecular weight. This formula can be shown on the right side, where the symbol of Mn represents the number of average molecular weight, and the symbol of N itself represents number of repeating unit. All this data can be found from NMR data results. This is the result of PLA product. The synthesis process conducted in the 80 Celsius and 3 days. After calculate the conversion of lactate, it shows in the table that all sample has high conversion number. The optimum lactate conversion of 99.59% was achieved by the sample that was rated using 2% catalyst ratio. However, the difference in the monomer conversion between samples was not significant. The number average molecular weight was estimated from NMR spectra, but some samples also tested using GPC to validate the calculated MN. The estimate MN, or average number of molecular weight, has different value compared to the MN measured by GPC. It could be happen due to overlapping between the longer and the shorter PLA in the spectrum, which makes estimating MN more difficult. However, the MN estimate from NMR may still be used for quick estimation. The highest molecular weight was achieved with value 292 gram per mole using 5% catalyst ratio. This is categorized as a low molecular weight. In the process, samples were participated in cold methanol, and there is no participate from, and the sample remain liquid. This can be caused by the low molecular weight of the PLA content and doesn't support for the formation of PLA crystal. Based on the table, the highest number average of molecular weight is 212 gram per mole, and the highest molecular weight of PLA is 292 gram per mole, achieved using 5% catalyst ratio. There is some studies show that the higher the catalyst concentration used, the higher the catalytic activity occur in the polymer solution, and produce higher average number of PLA. On the other hand, some other studies show that the larger the ratio catalyst used, the lower the value of the polymer. From this statement, there should exist one point for the optimum for catalyst ratio. In the beginning, the additional enzyme ratio can increase the catalytic activity until it reaches the optimum point. However, after passing through the optimum point, the catalytic activity decreases, affecting the MN of average number of molecular weight PLA result. In this study or in this research, increasing the catalyst ratio from 2% become 5% lead to an increase in the MN or average number of molecular weight of the PLA. Based on the table, the highest GPC of MN obtained is 212 gram per mole, and the highest molecular weight PLA is 292 gram per mole, achieved using 5% catalyst ratio. And the last part of my presentation is conclusion. The conclusion are the optimum operating condition have been obtained to synthesize PLA from lactate using Candida rugose and dimethyl acetamide solvent through ROP pathway. It was found that when ROP was performed at 80% and 3 days, and the optimal catalyst ratio was 5%. This operating condition gives a lactate conversion of 99% 0.47% with average number of molecule weight 212 gram per mole and molecule weight of 292 gram per mole.
Thank you, Ms. Cynthia, for the presentation. And we will continue to the next presenter is Miss Kiki Sembiring. She will be present the title Experimental Separation of Saturated and Unsaturated Fatty Acid from Hydrolyzed Palm Oil. Mr. Kiki, please start the video.
Good afternoon, everyone. I'm Kiki Cornelia Sari Sembiring from Research Center for Chemistry, National Research and Innovation Agency, BRAIN. We would like to share our board with the title Separation of Saturated and Unsaturated Fatty Acids from Hydrolyzed Palm Oil. We have known that Indonesia is the largest producer of palm oil worldwide. The data in 2019 showed that Indonesia exported about 55% of the global palm oil trade. Palm oil is the main feedstock for domestic food production, such as a frying oil, and consumer goods such as cosmetics, soap, detergent, etc. And recently, palm oil is used for energy source to produce renewable energy such as biodiesel production. Due to the huge daily application of the palm oil, today the research focus on palm oil are still being conducted, such as the physical property correlate to palm oil. This is the objective of our work, which is to understand the behavior of saturated and unsaturated mixture. And our works contain differential scanning calorimetry, DSA, of saturated fatty acid and unsaturated fatty acid mixture. In order to understand the liquid behavior of binary mixture. And our experimental separation of binary mixture of SFA and USFA. The last is experimental separation of multi-component mixture from hydrolyzed palm oil. Here is the method for separation. So there is a big difference between the melting temperature of the two systems, SFA and USFA. In SFA, the lowest melting temperatures is on the palmitic acid, 63.1 degrees C. And in USFA, the highest melting temperature is oleic acid, which is 13.4. Therefore, for this big difference, it is the basic of the separation. To simplify the experiment, stearic acid and oleic acid were used as models to understand the behavior study by DSC. This is the DSC measurement method. So the mixture of oleic acid and stearic acid in various composition were heat up to 90 degrees C at the rate of 10 degrees C per minute, then kept for 30 minutes, then cooled down to minus 30 degrees C at the rate of minus 2 degrees C per minute, and then reheat up to 90 degrees C at the rate of 1 degree C per minute. And this is the equation to calculate the mass fraction of stearic acid. There is the result from the SC analysis. So we got the curve of temperature versus fraction of stearic acid. Here we can point it to peaks at minus 3 degrees C and 13 degrees C, which are the peaks of oleic acid. And these two peaks show that there is a polymorphic transformation from gamma form to alpha form of oleic acid. While in the stearic acid, the melting temperature shifts to the highest temperature by increasing the fraction of stearic acid. And also the peaks became sharper by increasing the fraction of stearic acid. This shift due to the massive crystal matrix in the mixture. And this is the solid liquid phase diagram of stearic acid and oleic acid. So we can understand that solid liquid phase boundary exhibit a monotactic feature, which is composed of a horizontal solidus lines and liquidus line, which increase monotonously starting from the melting point of oleic acid and at the melting point of a pure stearic acid. So oleic acid and stearic acid are completely immiscible as a solid. And by this binary phase diagram, we understand that theoretically stearic acid and oleic acid can be separated easily. So this is the separation of oleic and stearic acid. The mixture was heat up at 80 degrees C, then cooled down to 30 degrees C and hold at 1 hour. And we separate it by a combination of filtration and centrifugation to get the filtrate rich of oleic acid and non-filtrate rich of stearic acid. Here is the separation. By cooling down from 80 to 30 degrees C, we got the cloudy white mixture, and by precipitation, centrifugation, we could get the white solid in the bottom. And after drying, this is the white solid of stearic acid. And the composition of the product in the filter, the oleic acid was about 93%, and still a small amount of stearic acid contained. But in non-filtered, the oleic acid was high, about 47.6, and stearic acid 52.4. The yield was oleic 72.5 and stearic acid 90.1. By this separation yield, to increase the composition in filtrate and especially non-filtrate, multiple separation is needed. This is the multiple separation method. Also, the mixture was heat up at 80 degrees C, then cooled down to 30 degrees C and kept for 1 hour and washed with acetone nitrate. And we separated by combination of filtration and centrifugation to get the filtrate and non-filtrate. So after first separation, we re-separate the filtrate and non-filtrate until 3-step separation. And at the end, we got the filtrate composition 93.3% of oleic acid, and in non-filtrate, we could get the stearic acid composition 97.5%. Here we can see that, especially in non-filtrate, the stearic acid content was high increase. And then we collect all the filtrate and non-filtrate separately. The total filtrate 75.8 and total non-filtrate 15.4. Actually, the yield decreased because the fit was 80 to 20.
Rolling with that.
And after that, we did the separation of hydrolyzed palm oil at 300 degrees C, 20 minutes. This is the composition of the hydrolyzed palm oil. Consists of triglyceride, diglyceride, and monoglyceride with fatty acid with a ratio of SFA 47.4 and USFA 41.0. 41.1. From the 1 gram of the feed, so we got a 43 solid and 49.5 liquid fraction, and 7.5 weight was lost. In the solid fraction, the ratio of SFA to USFA was 89.8 by 10%, and the liquid fraction, the ratio was 26 by 74%. So only rough separation was achieved by this method in a complex mixture. In the conclusion, the mixing behavior of oleic acid, stearic acid mixture by the AC showed the OA and SA completely immiscible. And the combination is needed by solvent addition in the experimental section. In a complex mixture, the separation yields rough SFA and USFA, and multiple separation actually increase the composition of oleic and stearic acid in the product, however, decrease the product yield. Okay, that's all my presentation today. Thank you very much.
Thank you, Ms. Kiki, for the nice presentation. Ladies and gentlemen, now we will have the last presenter. She is Ms. Retno. Will present the similar topic with Ms. Cynthia. Mr. Kiki, please start the video.
Good afternoon, everyone. My name is Retno Dita. Right now, I'm going to present my paper about the effect of reaction time on the synthesis of PLA from electrolyte using Candida rubus lipase and BEMI PF6 solvent through ring opening polymerization. And before we start, let me tell you about the outline of this presentation. So, we are going to discuss about the introduction, the PLA synthesis process, the result and discussion, and last is the conclusion. Okay, so we all know that plastic is one of the most used material in our daily life because of its durability and elasticity. Recently, biopolymer have attracted more attention due to the environmental concern and sustainability issues associated with petroleum-based polymer. One promising biopolymer is polylactic acid or PLA because it is eco-friendly, biocompatible, and stable. PLA also safe for biomedical and food packaging industry because it degrades by non-enzymatic hydrolysis in the human body, and its byproduct is eliminated through normal cell metabolism. PLA is commonly produced from the lactide through the ring opening polymerization route because it can produce high molecular weight PLA. ROP usually uses metal catalysts such as zinc, lead, and aluminum, and also organic solvent. But this often can lead to the toxic for our body and the environment. So, the enzymes such as Candida rubus lipase and solvent such as ionic liquid could offer an alternative for safer ROP pathway. Candida rubus lipase is commonly used in organic synthesis because of its high activity and specificity. It is also easy to be found and cheaper than lipase derived from other sources. Several studies showed that CRL was effective as a catalyst in the polymerization of monomers. The ionic liquid is a promising alternative solvent because it maintains the enzyme activity and stability, and it also prevents enzyme denaturation due to a high temperature because EL have polar and non-polar regions. Some studies showed that BME PF6 ionic liquid could increase lipases activity and selectivity. So, the PLA synthesis is consists of the polymerization and the separation process. Before the polymerization process began, we have to dry the CRL enzyme in a vacuum desiccator for 24 hours to remove most of the free water from the enzyme, while keeping the bone water, which will act as an initiator. Then, lactide, CRL, and solvent were added into a glass test tube. Then, the reaction mixture was placed in an oil bath at 80 degrees Celsius and stirred with a magnetic stirrer for a predetermined time of 2, 3, and 4 days. After the polymerization process was done, we are going to separate the enzyme from the mixture with adding 16 milliliters chloroform to the reaction mixture, and a vacuum filter will separate the CRL from the mixture. Next, the proton nuclear magnetic resonance, or NMR, was used to characterize the sample by determine the obtained structure, and gel permeation chromatography, or GPC, was used to determine the molecular weight. NMR data was also used to estimate the monomer conversion and the number average of molecular weight. So, this is the Anomaly spectrum of the product that obtained in 4 days. The spectrum showed that the signal for methyl proton resonance at 1.46 to 1.61 ppm, and the methyl proton resonance at 5.14 to 5.21 ppm. The signals belong to the repeating unit of the PLA. The peak of the chemical shift at 2.97 to 3.05 ppm represent the hydroxyl proton at the terminal group, while the signal at 4.35 to 4.41 ppm belongs to the methyl proton next to the terminal hydroxyl group. These NMR spectra of PLA were similar to the other studies, thus justifying the formation of PLA in this study. And the other peaks of chemical shifts belong to beaming peroxide ionic liquid, and these chemical shifts are also similar to the study than before. Okay. Next, the monomer conversion of lactate was estimated by NMR analysis using this question from Duchiron. So this value was determined by the integral of the lactate, PLA, and the N group characteristic peak from the NMR characterization, and the number average molecular weight also determined by the NMR analysis using this question from Izunabe, where ME is the molecular weight of the N-chain group, and MO is the molecular weight of the repeating unit, and N is the number of repeating unit, whereas the number of N or repeating unit can be found using this equation. With this is belong to the peak area of the repeating unit, and this is the proton number of the N group, and this is the number of the N group, and this is the peak area of the N group, and this is the proton number of the repeating unit. So, the calculation of the monomer conversion and the Mn of the PLA is shown in this table. We can see that the highest monomer conversion is 99.2% over the PLA obtained at 3 days of reaction time, while the lowest monomer conversion was acquired when the polymerization was performed for 4 days. The highest Mn value estimated by NMR is 599.4 gram per mole, obtained in 4 days of reaction time. Some of the sample were being further analyzed using gel permeation chromatography to validate the Mn NMR that had been calculated. And it turns out that the value of the Mn obtained by NMR and GPC are different. This could be because of the peak assigned to PLA might not indication of the sample molecular weight. The resulting PLA is categorized as low molecular weight polymer, as also proved by no PLA precipitate form when the polymer solution was precipitated using cold methanol. This could be happen because the polymer chain is too short. So this is the product of the polymerization. So the increase of Mn value is also followed by the increase of the polymer viscosity. The sample of for this reaction time was coming in gel form,
while the other were in liquid form. Such appearance is similar to some other earlier studies, and this type of behavior resulted from high initiation and propagation rates. No chain termination and monomer consumption followed the first order law. So, we can conclude that PLA, which obtained in 80 degrees Celsius in 4 days and with the ratio of feed and catalyst is 5%, have 91% monomer conversion and the MN anomer value is 599.4 gram per mole. That's all for me. Thank you so much.
Thank you, Ms. Retno, for the presentation. Ladies and gentlemen and participants, now we will start the discussion session. Here we already have one question for Mr. Dimas from Miss Amanda. I will read the question. What is C1 in FTIR spectra? I can see there was a distinctive broadband in OH bonding. Also, did you plan to characterize the thermal conductivity or insulation properties as the rigid PU form is mostly used in as insulation material? Mr. Dimas, please answer the question.
Okay, so thank you, Ms. Amanda, for the question. I will answer it.
Sorry, your
yeah.
Sorry.
Yes.
Could you speak louder?
Okay. Can you hear me now?
Yeah, more loudly.
Okay. Okay. For the first question, I will answer it. C1 is the result of mixing calcium carbonate with chitosan, which is cured at 100 degrees Celsius and 60 minutes. There is a very visible oxygen and hydrogen bond because the sample is not a fuse as the others. So it's very possible it's water that is still trapped. So the oxygen and hydrogen bond is very clearly visible because of the water. And the second question, yeah, my plan is to continue this research, especially the thermal conductivity characterization, because this is one of the important parts of the use of polyurethane rigid foam. Our plan will be from the best result from the foam composite, and then we will test it. We will test it in our campus laboratory. We will use some DTA, differential thermal analysis, and differential scanning calorimetry, DSC. That's all. Thank you.
Okay, thank you, Mr. Dimas. Miss Amanda, any further question?
No, thank you. Thank you for the response, Mr. Dimas.
Thank you, Miss.
Okay, thank you. Ladies and gentlemen, please, if you have a question, raise your hand and to the who the question is. Okay, not yet. Maybe if not yet a question, I will ask Miss Amanda about the rendement of the MFC. How many percent the rendement after the lignification, after bleaching, and the product?
Thank you for the question. For the question is around 40 to 30%, because as we know that the composition of the cellulose in the oil palm empty fruit bunch is around 30 to 40%. And during the bleaching process, we can get about 70% of yield. So in total, 50% yield from the oil palm empty fruit bunch to the microfiber cellulose.
Oh, okay. Okay, thank you, Ms. Amanda. Oh, Pak Jody?
Yeah, Mrs. Amanda. How are you in Italy now?
I'm
fine?
good, thank you. A bit jet lag, but it's fine.
Okay. Question in the chatting message and respond this question.
Okay, okay, thank you, Pak Jody. I also still reading your question. So basically, for the DSC maybe is useful when there is a big thermal changings in terms of our materials. But in that case, because we are doing some, I don't think so. There is a big differences in terms of the thermal changing in of the TG, for examples, and in that case, the most important properties that need to be conducted is the mechanical properties. Maybe there is a changing, but it's not that big changing. But we believe that our main purpose of this study is to enhance mechanical properties. So to study how the effect of microfiber cellulose in our starch-based biofoams, we have developed and investigated that the changing is corresponds to the changing in mechanical properties is correspond to the first the chemical interaction in terms of the hydrogen bonding between the starch and the microfiber cellulose, as well as we can see the direct morphology study. In that case, we can see that they are still challenging in terms of the blending process. So yeah, we still do the further characterization. And for the DSC, I'm not sure if this is really relevant for our study, but thanks for the suggestion. Maybe we can consider. But our first hypothesis that it might not have a great changing in terms of the thermal properties. Okay, Pak Jody, am I answering your question?
Yeah, as well clearly.
Okay, thank you.
Okay, thank you, Pak Jody dan Miss Amanda. Ladies and gentlemen, we still have a lot of time. Please ask your question to the presenter.
Maybe I can ask to Pak Jody. Jody,
okay.
I am actually curious how you determine the hydroxyl number, and what is actually the competing mechanism between the hydrogen bonding interaction as well as the surface morphology in terms of the BET, based on your results. In that case, in relation to the absorption properties.
Yeah, thank you, Ms. Amanda. So in this research, we also use the PVA as one of the absorbent here. As we know that polyphenol alcohol is the one of the polymer which have many more of the hydroxyl number. And we characterize the hydroxy number using the hydroxy number using the titration method. In the physicochemical chemistry, we saw that the PVA has more higher hydroxy number than the zeolite and AC. this indicates that the PVA have a more hydroxy groups in the surface of the PVA. Yeah. So using the chemisorption mechanism, also the mechanism have studied previously by our research also, that the chemisorption will occur in the hydroxyl groups in the surface of PVA with the ion sodium in the solution. Based on our previous research, but we can further research with the how we can measure the interaction of the hydroxyl number with the sodium ion with the maybe with the another characterization. But in this study, we not study, but in the further research, we will do the study. I think that this is your suggestion is very useful for our further study. Thank you.
Thank you, Pak Jody.
Okay, thank you Pak Jody dan Mbak Amanda. Ladies and gentlemen, is there any question?
Yeah, I have a question for Miss Cynthia and Miss Retno.
Oh yeah.
The chat box.
Miss Cynthia and Miss Retno, there is a question from Mr. Jody. What is the expectation of molecular weight value of PLA resulting from this research compared to the result of previous researcher?
Okay. I will answer question from Mr. Jody. What is the expectation of molecular weight value of PLA resulting from this research compared to the result of previous researcher? The expectation from my research is to gain high molecular weight of PLA, where the higher molecular weight I get, the more the better mechanical properties from PLA content, and this PLA can be used in many industries such as packaging industry or medical, etc. That's why we need to gain high molecular to require a good PLA product. I think that's it from my answer. Maybe Miss Dita could add another answer. Thank you.
So from me, it is the same. Our expectation is to get the more higher molecular weight PLA because the previous researcher he didn't use solvent. He doing the polymerization in bulk. So our expectation is when we use solvent, it could increase the molecular weight of PLA. That's it, Mr. Jody.
Or you can quantify that the value of the molecular weight that you have to be reached in this research. Is there any? Is there the molecular weight value is more enough than the previous researcher, or have to be developed in the further research?
So from our research, I think our PLA is still categorized in low molecular weight, so we still have to do more research for the further.
Okay, for your information that in our laboratory also we synthesize the PLA. So we expected that the molecular weight value is more than 1 million molecular weight mole per grams, that we have to reach that number of the PLA. Have you any expectation if you have developed the PLA to the higher molecular weight and of the application of the PLA also based on the molecular weight?
Mr. Jody, can you repeat the question again?
Yeah. In our laboratory, we have to our research is synthesize the PLA with the molecular weight around 1 million gram per mole. Yeah, and we want to know that your research, both research, what the expectation of the molecular weight in further research, your further research.
Okay, thank you for the question, Mr. Jody. First, I will mention that our study or our result experiment, the molecular weight that we get is still low molecular, but there is another consideration for the PLA synthesis is to result product non-toxic for human. That's why in our study, we need to gain high molecular weight of PLA, and then we must require for the non-toxicity for the PLA. And we in our study, we use a green catalyst and non-toxic solvent, and for my expectation for the future experiment related with my research is to gain high molecular of PLA, of course, and then there's another consideration such as it's safe for the human usage.
Okay. Thank you.
Maybe it's very interesting, Pak Jody, Ms. Cynthia, and Ms. Retno, because the research of Ms. Cynthia and Ms. Retno using the biocatalyst enzyme, but the molecular weight is very different with the Pak Jody result. Is million, and this result is only hundreds, kalau tidak salah ya. Maybe Ms. Cynthia and Ms. Retno have an idea what should be improved. For example, the condition or reaction time or something like that. Or maybe the other catalyst. I mean, are other enzyme or non-enzyme that more environmentally friendly to increase the molecular weight?
Okay, so I think we can increase the quantity of the lactide and the catalyst that we use, because in our research we only use 2.5 gram of lactide. So and the reaction time is only 2, 3, and 4 days. Now, I think for the further research, we should increase the quantity of the feed and the reaction time. So in hope we can increase the molecular weight too.
Okay, thank you.
I think it's clear.
Okay.
Yeah.
Okay, maybe is there any other question? Maybe before we close, I want to ask a simple question to Miss Kiki Sembiring, Mbak Kiki, about what is the further application of the separation saturated and unsaturated fatty acid?
Okay, thank you for the question. So actually, this is a one of section research of the renewable green diesel production. So in the production of green diesel, we use fatty acid, and then the fatty acid was produced by the palm oil hydrolysis, because if we can separate the saturated and unsaturated, so it will be the catalyst will be selectively run for the fatty acid only, not the unsaturated fatty acid. So actually, it is the objective of the whole research project. So it's only a little part of the section. It's a section.
Oh, okay. So for the green diesel application.
Yes.
Okay, thank you, Ms. Kiki, for the answer. Bapak Ibu, is there still any question? Okay, if not, I will close this session. Thank you very much for all participants and for the presenter for present this session. And on behalf of the committee, I would like to remind that tomorrow the seminar will begin at 8 o'clock. So let's close this session. Alhamdulillahirabbil alamin. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, see you. Bye bye.
Thank you. Paroni, so we can leave the room and we join to the main room, all right?